Our next speaker is Professor Zhang Baile, who's Assistant Chair, Research and Graduate Studies at the PAP NTU. His current research interests include waves in complex media, metamaterials, and photonic acoustic crystals. He has won many awards, including the 2012 MIT Technology Review TR35. Over to you.
Okay, thanks. Right, okay, thank you very much. I think I first met Prof Phua in roughly 2013 in a special workshop organized for high school physics teachers from Malaysia. And I was very impressed at that time because I tell myself that, okay, he's really devoting himself to promoting physics education. I wish I could have 50 years research journey in physics. So far I don't have. I only have 10 years. So over here I will share with you my 10 years research of scattering free metamaterial from invisibility cloaking to topological photonics. So let's first watch a short video clip. This video clip is a short one from this video entitled Metamaterials, the Next Photonics Revolution, casted in 2009 by the Optoelectronics Research Center in University of South Edmonton. Okay, later I will explain why I chose this video clip.
The gunships closing on their target quickly. They will be in firing range very soon. Realizing they have been caught by surprise, the tanks switch on their metamaterial cloaking devices and vanish. Now the gunships are vulnerable. They back off and retreat. This is Star Trek science fiction. But in the 21st century, real science is not far behind.
Right, okay, you can see that over here we hear a few keywords. Okay, the first one is metamaterial, and the second is invisibility cloaking, right? Sounds very weird. And also you can see that, okay, this is from University of South Edmonton, and this especially overseas, the Optoelectronics Research Center was a leading center in the field of metamaterials. So why I choose this video, okay, so at that time, okay, I joined NTU in 2011, and I was told that NTU would like to support photonics, so they will set up a new research center called Center of Disruptive Photonic Technology, CDPT, under support of a Tier 3 program. And Prof Zhang was very supportive at that time. So in 2012, the center was officially opened. So you can see that this is the first director was from South Edmonton. We invited the Prof Nikolai Zedodev to be the first director. So he's over here. And then Prof Su Guanyin was over there also, and Prof Bertil Anderson was also over there. So. And nowadays, okay, our center is pretty large over there. So we have 11 PIs, okay, and 38 research fellows, okay. And then Nikolai was a director, and Prof Zhang is a co-director over here. And I was among the first few PIs in the center. And at that time, I still had this baby face, but now it looks much better now. So first of all, what is a metamaterial? Right? Okay, so it's I think so far there's no precise definition of what is a metamaterial. So generally speaking, right, metamaterials refer to those materials that whose properties originate from the structure rather than the composition. So for example, if you consider a common material, let's say a piece of glass, right? So from the viewpoint of the electromagnetic wave, okay, this material consists of a lot of molecules or atoms, right? So you can treat them as electric dipoles. Okay, on average, they will give you the refractive index. But for the metamaterial, let's say if you put a metallic rod, for example, to induce a dipole, electric dipole, so you can create a lot of electric dipoles. And also, on the other hand, if you introduce a metallic loop, for example, right, you can create a current loop to induce a magnetic dipole. So you can have both electric dipole and magnetic dipole designed by yourself. Okay. So what is the use of it? Okay. So over here you can use the electric dipoles, right, to create the permittivity. For example, you can let the permittivity to be negative. This is plasma, right? And on the other hand, you can also induce a magnetic dipole. Okay, so you can change the permeability of the material. Okay, to introduce a magnetic plasma and to change the permeability to be negative. So if you have negative permeability, put them together, you have negative refractive index. So you can, if you think about the Snell's law, then the refraction will be negative. Okay, so I think in the first 10 years of this century, the whole field of metamaterials was focused on the negative refraction, this kind of research. So why it matters, right? Why it matters? So if you think about how we design, right? how we utilize the materials in the history, we always start from material. We look at what kind of properties this material can give us. Then we try to develop some kind of function based on the material, based on the knowledge that we can have from the material. But the metamaterial design is reversed. Okay, we first think about the function. What do you want to do? And then you look for the material, okay? If the material exists in nature, that's good. If it doesn't exist in nature, then we build it, okay, artificially, right? And then, okay, let's say if you really have no limitation on the materials, let's say we can have arbitrary value of epsilon and mu, this kind of optical parameters, what we can do. For example, this is I think a typical example is invisibility cloaking, right? For this, then it's no longer a science fiction over here. It can be a scientific problem. So let's say, okay, if you consider free space, right? This light ray will propagate along a straight line. Okay, this is high school physics. And now this is Cartesian coordinates. And now we assume that the space is flexible, so you can distort it. Okay, you can do whatever you want. So after the space distortion, then you can see that the background is distorted. This is the coordinate transformation over here. And then what happened to the ray is distorted together with the background, right? So we know the Maxwell equations are form invariant, okay, in different coordinate systems. So from here to there, you can convert the space distortion into the change of materials, all right? Basically, you can convert the space distortion into the epsilon and the mu, okay? So in other words, if we can build the epsilon and mu by design, we can use the build materials to simulate this kind of space distortion, okay? For example, if you consider, okay, if you take the volume of a sphere and then squeeze the space into this spherical shell, then you can bend the light around this spherical region, okay, without touching it, and then anything hidden inside will be invisible. So this is a proposal, theoretical proposal by some, back to 2006 by some very famous scientists, including, for example, Prof Zhang from Imperial College at that time. So this is some background about invisibility cloaking. Nikolay, okay, Prof. Nikolay Zolodev, he also, okay, that was around 2011, right? So Prof. Nikolay Zolodev also published a roadmap, okay, for the roadmap ahead, the road ahead for metamaterials. And over here, he described the trend of the research field of metamaterials. I think it is general one. It applies to any field, okay, in physics. So over here, the horizontal axis is the time, and vertical axis is the research, research effort. You can treat it as an enthusiasm, right? So you can see that in the beginning, right, when there's new discovery over here, you can see that in the beginning, the enthusiasm or the research effort quickly increases over here, and then until you reach the peak of hype. And then you suddenly jump over here. And then after a while, this is for the sober assessment. They will start to arise again, but this is very hard work. Okay, you need to really look for the applications, right, for the systems. And you can see that, okay, since the first concept of invisibility, right, and then you can imagine there's a huge of interest. And then this is already 2011. So you can see that the transformation optics, right, metamaterial over there, has already passed the peak of hype. And then you can imagine that after that, okay, in the next few years, we will go through this sober assessment, and then I think nowadays we are roughly over here, right? We are roughly over here. So in the next few years, right, back to 2011, we already see different responses, okay, in the opposite extremes, right? On one hand, we can see that, okay, this research has, the topic of invisibility was listed top 10 breakthroughs of 2006, right? And then at that time, there are already a lot of papers in the top journals. And also, there are storm of reports in public media. There are a lot of public reports in the public media. But on the other hand, okay, we see the different response from the including scientific community. For example, there's a IEEE conference. You can see the title of the paper, the IF, radio frequency invisibility using metamaterials, Harry Potter's cloak or the Emperor's new clothes, right? And then, okay, this is from a founding agency. Okay, in my early years over here, I will never invest a penny in cloaking research. Okay, and then back to 2012, I was in a kind of interview, and then there's an eminent scientist told me that you have made a big hype. So. Typical criticisms, okay, you include, for example, okay, it has math problems, right? It violates causality. Okay, this math problem, okay, you can imagine this criticism is from mathematicians. Basically, this transformation, right? You can see that the original derivation is non-singular, but the transformation that create a cloak is singular. Okay? How can you apply a non-singular theory in a singular case, right? And then you don't know how to apply the boundary condition to begin with to do the calculation, right? So you need to solve it, and then for the causality problems, I think I provide some answers in my PhD thesis, right? And after my PhD, then I start to think about, okay, whether can I provide some solutions to other problems? Okay, for example, it's possible only at the nanoscale. Can we do it in a large scale? Can we do it with a very broad bandwidth, right? Can we do it for some realistic application? So this is actually my first experiment, and you can see that this is over here. This is this pink color. Okay, is a Post-it note. So we wrote it up. You can form a paper roll and put it on top of this. Just the middle over here, and then we can move these two pieces of calcite to form a cloak and cover it. So you can see that the covered part becomes transparent. Okay, you can see that, but you can see through directly, right? So this is a simple demonstration of invisibility, but you can, at a large scale, okay, macroscopic scale in the visible light. But it follows strictly, okay, it strictly follows the transformation on the right-hand side. Okay, there's no problem from the transformation point of view. Mathematically, it's okay. So this was my first experiment, actually, and I was surprised that it was listed like a top 10 breakthroughs by the physics award at the time. Although it works over here, you can see that we immerse it into oil, okay, to slow down the lights, okay. But you can see that the limitation is still there. So where's the limitation? The limitation is that when you bend the light around the curve, the trajectory, in order to recover it at the shadow, so you can see that you must require the phase to propagate faster than the speed of light, right? Okay. So you can see that. If the phase velocity propagates faster than the speed of light, it must be narrow band. Okay. So next, what do we do? All right. So let's forget about the laser. Let's forget about the coherent light. Let's just use incoherent light because this is the most natural light, right? So we say, okay, let's get rid of the phase. Let's forget about the phase preservation, right? Then we don't need to conserve the phase. Then we can create it in a broadband. At least, right? At least you can do it for a few different directions, right? You don't need to preserve the phase over here. So you can simplify the design, okay, a lot. So you can see we did it in this experiment. Over here you can see there's a tail of the fish over here. Then you can see this fish head over here. Okay. It's still alive, so it's still breathing. The fish likes stay inside, so we try to kick it out. Right. So you can see that as long as you don't need to preserve the phase, you can simplify the design quite a lot. And the next thing we think about, okay, that does not require phase, that does not have phase to begin with, is the heat, right? Is the heat transfer. So we did this experiment. Over here, you can see this is at the bottom. This is the heater, and then we have a piece of stainless steel. This is a bulk of stainless steel over here, and then on top of it, this is actually an ice tank. So later, when I turn on the heater, the heat will transfer from the bottom to the top, okay, homogeneously. So over here, okay, in the second example, we dig a hole. Okay, this is an air bubble over here. So we know the air is not a good thermal conductor, so we'll block the heat transfer. So later you will see that the heat will start to accumulate at the bottom, but there's supposed to be a shadow at the top. So on the top surface, this will be relatively cooler. But you don't want it to be cool, right? Because this is the starting point of most thermal failure, actually. So over here in the last example, okay, we try to compensate this air bubble over here. Okay, we say this is a thermal cloak over here. So we try to hide it. We try to hide it from the heat transfer. So let's see the performance. This, of course, this is taped with a thermal camera. So in the first example, you can see the heat transfer, okay, from the bottom to the top, homogeneously. And then over here, this air bubble has blocked the heat transfer, so you will end up with a relative, you could call it a thermal shadow, okay, on the top. And over here, you can see that it has been recovered. The heat transfer has been recovered in this case. And this is because you don't have the phase, okay? You don't need to worry about the phase to begin with. All right, so you can see that, okay, number one, if you don't need to preserve phase, you can simplify the design quite a lot. So the next one is, okay, can we slow down the light, right? Can we slow down you don't need to always propagate with the speed of light, but there are so many different waves that moves quite slowly. So we start to think about the surface wave. For example, if you consider the interface between a dielectric and a metal, you will have surface wave, the so-called surface plasmon polaritons. And then there's a huge limitation over here is that as long as these surface plasmons or the surface waves meet these obstacles or these sharp corners, there will be scattering. Right? There will be scattering. The wave will be scattered in the air, in the surrounding environment, and because of the momentum mismatch over here. So so far, this is known as the scattering loss. The scattering loss is treated as an intrinsic limitation in photonics. So we designed this corner cloak, so try to hide the corner. So from the viewpoint of wave propagation, the waves will be treated as if it's still propagating on a flat surface, right? So we did the experiment over here. So let's see the video, okay, the simulation over here. So the first example, this is the two sharp corners without any cloak over here. We didn't do anything, so you can see the wave will be scattered. But over here, okay, after we add this corner cloak, so we can guide the pulse through these two sharp corners very smoothly, as if the wave is still propagating on a flat surface. Okay, from the viewpoint of the wave, it doesn't feel that it doesn't feel any difference between the second case and the flat case. And we also build this bump. Okay, how about we have a bump? And then we also create this copy cloak, right, to cover it. So let's try to watch the video. Again, in the first video, you can see that over here, there's a bump over here. This bump will scatter the energy, most of the energy into the surrounding environment. But for the second case, you can see that the pulse, okay, this pulse can go through this bump very smoothly, as if it's still propagating on a flat surface, okay? So over here, you can see that the scattering loss can be suppressed, okay? It's not an intrinsic limitation in photonics. You can do it. So why this is related to topological photonics. And later, okay, after I joined NTU, and then after a few months later, we have a new colleague, my friend Dong, okay, over here. And actually, we graduated the same year from MIT, but I never met him before until we both joined NTU. So he shared with us his previous work, actually in his PhD thesis as well. This is a photonic crystal. And then you can see this photonic crystal contains a lot of gyromagnetic materials. You apply an external magnetic field to bias it, to break the time reversal symmetry. You can create a band gap, photonic band gap. And then what is very interesting is that over here, if you calculate the chain number, it will be non-trivial. So we say it has a non-trivial topology. And then if you put a source over here, this is the antenna, then you can see that you can launch an electromagnetic wave propagating all the way to the right-hand side without being reflected back. Even if you meet obstacles, okay, even if you meet obstacles, you must move forward. You cannot come back. This is like an order. So this wave can only propagate around this obstacle and keep moving, as if this obstacle does not exist. Then I say, hey, isn't this the same thing as what I'm doing here, right, over here? So we start to collaborate in the next few years. Can we do something interesting together with topological protection? So The first thing is that, okay, we try to introduce Baile as a new degree of freedom into photonic crystals. So we, over here we have many experts in electronics in 2D materials. So Baile is also a binary degree of freedom widely found in 2D materials, similar to spin. You can use spin to introduce a band gap. You can also use Baile to introduce a band gap. So over here, we firstly introduced Baile to introduce a photonic band gap. I think this is the first time. And then, we can demonstrate the robust propagation along this zigzag path. So what is very different is that over here, if you talk about, if you think about topological materials, right, all the electrons will not all of a sudden jump into vacuum, right, because of the work function. But photons can. And they can do it with 100% perfect efficiency because of the topological protection over here. And then this work was done in 2018. And 2 years later, we also collaborated with our colleagues to build a laser. Okay, this is from Chijie's group, and Chijie and the Renjun, okay, in terahertz frequencies. Both of them are CDPD colleagues over here. So Chijie's work is a quantum cascade laser. Okay, this is extremely robust based on the previous Baile photonic crystal. And also, the Renjun's work is a chip to boost the communication speed. Okay, you can achieve an ultra fast on-chip communication. Okay, this is extremely useful for future 6G communication, right? Okay, and okay, talking about topological insulators, we know that there are 2D topological insulators, right, and then 3D topological insulators. So if you preserve time reversal symmetry, the 2D topological insulator can have edge state going around this edge, like, polarized by the spin. So if you have spin up, you will propagate along the edges clockwise. If you have spin down, you will propagate counterclockwise. And then you can also extend it into 3D, right? 3D. So you can see that on the surface, okay, you will have surface topological surface states that can form Dirac cones, right? Dirac cone surfaces. Okay. So now let's keep in mind that when I talk about time reversal symmetry, this time reversal symmetry is only for fermions, right? For electrons. But photon is boson, right? So the time reversal symmetry is different. So how to construct a photonic type of three-dimensional topological insulator with this kind of Dirac cone surface, topological surface states is different. It's completely different because you can see that fundamentally even the time reversal symmetry is different. So we built it, okay? We designed this metamaterial structure over here. Essentially, it's a photonic crystal over there. So we construct it, okay? We construct this domain wall over there. There's a surface, and then we do the measurement. So you can see that, indeed, we can observe that, okay, this surface states can exhibit the Dirac cone. And this is the first time that a topological insulator is implemented for a boson, a three-dimensional boson systems, bosonic systems. Let me remind you that, okay, the field of photonic crystal was established because of the pursuit of a three-dimensional photonic band gap through a very complicated exchange between theory and experiment. And over here, we are building a three-dimensional photonic band gap with topological properties. Since we talking about topological insulators, okay, we also have topological semimetals. So for example, you have a wear point, right? So the wear point is a point degeneracy that can simulate the behaviors of wear fermions. Wear fermions is a hypothetical particle in high energy physics, but still couldn't find in nature. But we can study it in crystals, okay, as a quasi crystals, quasi particles. So over here, you can have a band degeneracy, so-called the wear point over here. So the wear point is also characterized with a Chen number. So you can have positive Chen number, and negative Chen number. And then if you have projection on the surface, then you can have surface states that connect them, okay, through this so-called Fermi arc. So you can see that because the wear particle is, the wear point has a positive charge and negative charge, right? They always appear in pairs. And then they are connected by the Fermi arcs, right? So you can see that, you can imagine that, the simplest configuration must be that you have one positive wear point, the other the negative wear point, connected by a single Fermi arc. This is, of course, the simplest configuration. But it turns out this is quite difficult to achieve in reality, right? So far, all the wear points realized in condensed matter, you can only observe 4, all right? okay? And then in order to observe two wave points connected by a single Fermi arc, you need to break the time reversal symmetry. So you need to go into the magnetic wave semimetals. So we build a photonic crystal, okay, with the magnetic materials. Basically, we just stack up the 2D magnetic crystals along the third dimension. And then you can insert a probe and source, right, to measure the transmission through the bulk. So this figure shows the transmission. Okay, the color represents the transmission. The horizontal axis is a magnetic field because we apply an external magnetic field to bias it. The vertical axis is the frequency. So you can see that in the beginning, when the magnetic field is pretty low, right, we have a band gap. This is a three-dimensional photonic band gap. And then after you increase the magnetic field, the band gap is closed. You will enter the wave crystal phase, okay, wave semimetal phase. And then after you further increase the magnetic field, this right line represents the frequency of the wave point. And after you further increase the magnetic field, right, after you reach this threshold, this band gap is further reopened, okay? But later you can see that we will enter this so-called 3D Chen-insulator phase. So in terms of surface states, you can see that in the beginning, when the magnetic field is 0, there's nothing there, right? And then when you start to increase the magnetic field, okay, you enter the wave semimetal phase. So there's a single Fermi arc over here. So this is the most clean situation over here, because the condensate people, they are looking for a clean environment. This is the most clean, right? You only have one single Fermi arc. And then you further increase the magnetic field, you will stretch this Fermi arc toward the boundary of the Brillouin zones, and then get annihilated. And then you can see that it will form a Fermi loop over the entire Brillouin zone, and the band gap is opened. Okay, band gap is opened. So, because here you have a 3D band gap, all right. So you can also, previously for 2D, you can use a Chen number to characterize it. Okay, looks similar to the quantum Hall system. But over here, this is a 3D system. So you need to use three Chen numbers at the same time, okay, to represent it, to characterize three perpendicular surface cross sections. So you will end up with a Chen vector over here. Okay, so over here we calculate the Chen vector is a 0, 0, 1. So it represents, because this is the torus, you can see that you represent a torus that's wind around the Brillouin zone this way. Okay, so over here you can see that this one is a non-trivial Chen number. So over here you can see that this Chen number is not just a Chen number, because this is also a Chen number with directions. So Chen number can also have a direction, but how do we illustrate the directional property? So let's consider two photonic crystals. Okay, on the last slide I have shown you that we can have photonic crystals with directional Chen number. So let's say we have two photonic crystals, okay, with an interface. This Chen number is along the z direction, this Chen number is along the x direction. And then let's see that what happens over here. So it turns out that if you have a Chen number that is along z direction, the surface states, on the last slide I showed you that this is correspond to a winding, Fermi loop, wind around the Brillouin zone, right, the torus. So if you change the unit, we change the amplitude from 1 to m, let's say, so the winding will be m times. And now if you have this Chen number along the x direction, so it corresponds to the winding along the longitudinal direction, right? So you can see that you will have two parameters to characterize the surface states. Surface states over here. This is the m, this is the n. So if you say this m and n, they are coprime, then you will form torus knots. And if you this m and n, they are not coprime, you will have links, torus links. Okay, and then the number of components for the links will be determined by the greatest common divisor. So over here we just illustrated it as a 2, 2 over here. So of course the greatest common divisor is 2. So we have the simplest link. Okay, simplest link. This is so-called Hopf link. So we did the experiment. You can see that this is the measurement in the surface Brillouin zone. Okay, if you put it on the torus, you can see that this is indeed a torus link. So why this is important? Previously, when you talk about topological surface states, it's either Dirac cone or a Fermi arc, right? What else? No, you can have more complicated topology even for the topological surface states. You can form this kind of non-trivial torus knots or links, okay, based on the different parameters. So yeah, this is a summary of my 10 years journey of research at NTU. We start with invisibility cloaking, and then we also start to involve with topological photonics. Okay, I record my first part as a geometry, but later okay, you can see that this is more related to topology. Okay, thanks.
Okay, thank you, Professor Zhang. Are there any questions?
Yeah, time for dinner.
Yeah, I think it's getting late. So if you have any questions, please approach Professor Zhang separately. Thank you. Thank you once again for the talk.